Okay. I would like today's class. Well, we've we always could cover more material, but actually, even though I'll let you know about the exam or what the schedule for the exam is next class. I'll have to think about it. How much material? It depends how much time I spend using classes for just practice problems and so on. So I'll think about it. I'll let you know in the next class what the schedule will be for the exam. I know I always tell you at least a week in advance, so you don't have to worry about it being right away. Also, there is still a little bit more of material that should go into the exam, so we're not there yet. But I still, nevertheless, I would like to spend a little bit of time doing practice stuff, just because I realize that this right-hand rule is not that it's very hard. It's just that is a 3D thing, you know. So when you start doing this in 3D, then you have to match the words in the question to the 3D picture, you know, computers and tables and things like that, and it slows the process down when you start doing the right-hand rule. So I like to do a couple of examples just to get you a little bit more comfortable with it. Maybe some of you are comfortable already, but there's always the 3D thing that stops people from being fully, you know, like being really quick about it. So I do want to go over, you know, so I said 3 examples, and then we could actually, you know, there's also a little bit more on this Ampere's law. So the solenoid is very important. I should cover the solenoid. It's kind of, as I mentioned last time, the solenoid is the capacitor of magnetic fields. You could think of it that way just to remember. So we didn't really go into what should the magnetic field inside a solenoid be. The only thing I said about that is that if you have a solenoid, which is just a wire, you know, wrapped up around the cylinder, that if you have that situation, and we're going to encounter it in a second, but let me just say that the only thing that the reason why it's like the capacitor is because when we talked about the capacitor, the electric field inside was constant, and the electric field outside the capacitor, 2 plates, not 1 plate, 2 plates, 1 positive, 1 negative. Then the electric field outside was 0. And the reason why that happened was for plates was because the electric field ended up being independent of position, of distance from the plate, because the plate was supposed to be infinite. And so since you have 1 on top, 1 on the bottom, outside the plates, they cancel out. Inside the plates, they result in a constant electric field. So the solenoid is a similar thing for magnetic fields. Inside the solenoid, which is just a wrapped up wire, the magnetic field is a constant, and outside is supposed to be 0. Okay, we'll go to the derivation. It's kind of like an Ampere's law, but more important than that, that's important actually. I'm not saying that's negligible. You know, basically these solenoids then get put into circuits, and then you talk about the inductance of the circuit. So when we get to RLC circuits, we'll have 3 elements in there: the resistor, which we're familiar with, then the capacitor, which we're also familiar with, and then just the loop wire, which will store magnetic fields. So yeah, of course, you know, you're implicitly, you know, when you get to that part, you actually don't need to rework the theory of solenoids, but implicitly, just like capacitors are being used in capacitors in the wire in the circuit, and that's RC circuits. Then we'll add a little solenoid into it, and then we'll have RLC circuits, and those are a little tricky. But yeah, solenoids are the foundation of that. It's not like you absolutely, you know, you will use the formulas when you get to it anyway, but, you know, it's nice to know where it comes from. It comes from having a wire looped around and a changing current. Okay, well, we'll get to that. So anyway, we do need to have the B field of the solenoid. That's the bottom of this chapter. But more practical than that right now. Certainly for the exam, more practical. Later on, RLC circuits won't be in this exam. RLC circuits will be in the final. and I will be very, very constrained about that because I will run out of time, won't be able to do the full RLC problem. So I'll just give you a very specific instructions about what about RLC, basically just in series, and that's it. We'll get to that later. Anyway, right now for this exam, yeah, you do have to practice the right-hand rule, make sure you got it right. Let's actually, instead of doing it through the PowerPoint, we can come back to the PowerPoint to see if the drawing agrees with us or not. But again, just for the sake of preparing you for the exam drawings are not going to be in this format, like a 3D drawing. That actually, more than not, actually most of the time it confuses people because 3D is not clear which direction you're pointing sometimes, or to the left or to the right or something, what's behind, what's in front. For exams, it's much better, in my opinion, to just keep doing the same drawings, which are flat, look like 2D, but then there's also in and out from the page. So that's the 3D then. Okay, so let's do that again. And let's see if, based on what we've said so far, let's see if we already have the right ideas for things. So let's just leave the PowerPoint. We'll come back to it, okay? But I would like to do two different problems without the PowerPoint. Well, let's just start with the one. So which formulas we're going to need here? Well, we already get, so just to tell you where the formulas come from, we derived this formula with Ampere's law. Now, here in this PowerPoint, they derived it two different ways. Please keep that in mind. When you're looking at this formula, it looks like they're doing something very complicated here. And they are, because they're using an integral. And then, so let me just, remind you, maybe you forgot how this went already, because it's a little confusing. This PowerPoint with what are you doing here? Then you have Ampere's law. What is the connection? The same thing happened with Gauss's law. So the PowerPoint is a little, it's not linear thinking. It's kind of like, so what they're doing here is they're starting from this Biot-Savart law. So what the hell is the Biot-Savart law? Okay, we already gave that. That's this law. Well, this is the wire form of the law, and this is the not wire form of the law. Okay, so this is the Biot-Savart law. It says that a moving charge produces a magnetic field. And we went through this R hat, that's why this is all marked up and so on. Then, so I'm kind of like reminding you of where we are. Let me take a little bit of time, but then we'll get practical, okay? For sure, that's the goal today, to get practical. To just pick examples and you tell me what it means. And then if you don't know, then of course I'll help you, no problem. So anyway, so this is what we did. We said, okay, we start with a moving charge. The charge is moving. And then we say a moving charge has a magnetic field, produces a magnetic field. This is chapter 28. And then we spend some time thinking about that R hat. What the hell does that mean? And we figure out that's a unit vector that points between the moving charge to the point in space that you're interested in. Okay? And this formula with a cross, so already whenever there's a cross, there really is a right-hand rule right there. Now, we're not going to use this formula so much, but if you did use it, then yeah, then you would still need the right-hand rule whenever there is a cross product, right? So put your fingers in the direction of the first vector, you cross into the second vector, the thumb points in the direction of the resultant field, the resultant vector. In this case, the magnetic field. Okay, anyway, so we're going to definitely use this formula. And we could use this formula for the example of the two protons moving right next to each other. And we'll come back to that. First, let's do the easier example, which is the two wires, okay? So this is the two protons. If you wanted to do two protons, and we will do that one too next, that will be the second example. But if you wanted to do two protons moving side by side, then you would need this formula that we have in front of us, because this formula is for a moving charge. Well, these are protons. They're moving charges. So you would like to know the electric field due to the moving charge. Okay, that's easy. But then you have a magnetic field, which is given by this formula. And let me just anticipate a little bit. We're not going to do this case first, but in this case, suppose you have two protons. We'll come back to it. you have moving side by side. Let's just to, again, demystify this R hat. What R hat would we be talking about when we have protons moving right next to each other? Well, what I'm interested in when I have two protons moving right next to each other is the B field of one proton, which is moving, on the other proton, which is also moving, right? We're just to keep the example as simple as possible, we're going to move them with the same speed. So they're always kind of like side by side. That's the assumption to begin with, see if that works out. But in any case, so what we're interested in is the B field of one charge on the other moving charge, right? So you want to know the B field, say it doesn't matter which one you take. You can take the top one or the bottom one, who cares? So we can call this charge 1 and that charge 2. They're both the same, so it doesn't matter which is which. So I can pick charge 2 to produce a field on charge 1. Okay, so I need to know, therefore, the B field due to charge 2, so let's call that B2, on charge 1. Well, to know that, I need to know R hat. So I need to follow the prescription. So what is R hat again? It says in the PowerPoint, is the unit vector from the point charge toward the point where the field is to be measured. Well, in this problem, we're interested on the force between the protons, the magnetic force and also the electric force. The electric force we already had from before, that's easy. That's just Coulomb's law. That's KQ squared over R squared. But for the magnetic piece of it, we need to know the B field of charge 2 at the location of charge 1. So the R hat is the little unit vector pointing from the charge you're calculating the field of to the location of the other particle. So that would be your R hat. And it's a unit vector. So it doesn't have a magnitude of 1, right? So that's it. That's what R hat means in this situation. R hat is always determined by the point in space you're interested in calculating the magnetic field. Okay, the point where you're calculating the magnetic field. Well, in this case, you're calculating the magnetic field at the location of the second charge. So that's why R hat is that direction. Okay, we'll come back to this. Let's go back. We really need to be clear on this. So my goal today, this is what I'm going to do. I'm going to do two wires, the two charges. So we're going to need this formula, okay, to do the two charges case. In fact, I'm gonna give you a chance to do it yourselves. We're gonna do the two wires together. I'll do most of that. I'll use the wire formulas, and then I'll ask you, okay, what do you think? I'll ask you a question about two charges. See if you can figure it out. Give you a little bit of time to try to figure it out instead of me just giving you the answer. And then we'll work on it together if you didn't get it or whatever. And after that, what I think we should do is go to the test bank for chapter 28. The test bank for chapter 27, it would be also useful to do. They're both on Canvas. So I got that from Master in Physics. I downloaded that from Master in Physics. I put it on Canvas. For these two chapters in particular, it is useful to go through those test banks because it forces you to do the right-hand rule 10 times, 20 times, 30 times, and then, yeah, okay, you got it, no problem. So I would like to start that off. I don't know how much of it I'm going to do, but okay. So anyway, so we'll do these side-by-side protons, and then we'll also do the side-by-side wires. And the side-by-side wires, I guarantee, is going to be in the exam. This one might also be in the exam, the side-by-side protons moving instead of wires, protons. They're moving charges, but they're pretty much the same thing. It might also be in there. I'll have to think about the time constraints. So I might put it in or not, depending on whether I feel that you have a chance to finish the exam. So if the exam is too long, then that might be the one. Since I already asked you about the wires for sure, then I might decide, oh, let's not put the protons. It's slightly different, but it's a similar type of problem. I'll have to figure that out. I don't know yet. Okay, anyway, so let's do the two wires one. We already got started, but again, let's go from scratch. So what do we have to do for the wire case? So this formula is for a moving charge. So the next thing in the PowerPoint they do is to change that formula into a current. But moving charges produce current. So of course there is a direct connection between a moving charge and a current. Now, if you do it in general, the B field has to be integrated. So if you have a wire that keeps changing directions and so on, and the direction of the current keeps changing, then you have to do an integral. That's what they're telling you here. But we're going to try to avoid doing integrals. But here they're saying, okay, in general, yeah, if you have a wire, this is a differential equation as dV, the derivative of the B field, and dl is the little chunk of the wire. Take a little chunk of the wire, you calculate the effect of that little chunk of the wire. It's a vector, so you got to calculate the magnitude, you got to calculate the direction, x direction, y direction. And then what they do next is they say, okay, great. Now let's take a very simple example and integrate it. Now, this is a simple example, but if you integrate it, it's not so simple. You know, you got to do an integral. It's not, you know, we're not going to spend the time doing integrals here. You know, to be honest with you, everybody should have calculators now that do integrals immediately. I'm not sure why we haven't gotten there. Online, you know, Mathematica and all of those, Mathematica is very good at it. It gives you immediately a closed form, not an approximation. It gives you the solution. So there are all kinds of programs out there that do that. So maybe at some point we should have, you know, calculators that have that already. And then you could do integrals without wasting any time, because the integral, the calculator gives it to you immediately. But anyway, you could do that in the computer, but you know, whatever. We're not doing that, so we're avoiding doing integrals. But let's think about the direction that they're telling you here. They're saying, look, when I calculate, look at let's try to understand this diagram without solving the integrals. We're not going to need to solve the integral in the end. I told you that, but I'm just reminding you of how we got the formula. We said, look, you could get the formula from a wire. You want to know the formula from a wire. So I want to know what is the B field at this location. Well, so far I only have dB. I don't have the actual value for the field. So I take a little piece of the wire and I integrate it up and down from the center, from location 0, and then they say we're going to make the wire go off to infinity. Just remember how we make the plates go off to infinity to preserve the symmetry. So they're going to do the same thing with Ampere's law here. The wire goes off to infinity. Otherwise, the formula we use doesn't apply. If it goes on to infinity, then yes, you can use this formula. Okay, that's the approximation. That's what you're assuming to get this. Okay, but anyway. But it's not just the magnitude. Let's look at the direction. The current goes this way, right? And the B field is into the page. You see that it's showing you a cross here. How do we know it's into the page? Well, remember again that we did use another right-hand rule here. I mean, we can use it using this. What do? I like to write dl cross I cross r, but it's the same thing. They're saying dl cross r hat. So, okay, great. So based on the piece I have, so look at the drawing r hat. R hat points between the piece I'm considering, this is the piece I'm considering of the wire, and the pointing space I'm interested in. I'm interested in that point right there. I want to calculate the B field at that location. Okay, so then the r hat, as I integrate, I pick another piece there, and so on. As I'm integrating up the wire, r hat keeps changing. You gotta do an integral. But anyway, there is r hat. So then I say dl cross r. So I do my right-hand rule. So it's dl and then cross r, and that points into the computer screen. R points down, so I'm like the wire is straight up. So DL is, my fingers go up, that's DL. My wire is pointing straight up like the computer screen. Then DL is up, so my fingers are up. Then I have to cross it into R hat. Well, R hat points to the pointing space I'm interested in. Okay, and then my thumb points in the direction of the B field at that pointing space. So that says into the page. Is it into the page here? Yeah, of course it's into the page. That's the cross means into the page. Okay, we're not really there yet. that we know the direction and we know the magnitude of this one, but you still have to do the integral. Well, they do the integral for you. You don't have to do integrals. They tell you that you get this when you do the integral. And then the next step they took, which we're not ever going to need to do because we're going to use Ampere's law again. I'll remind you again about Ampere's law, what we did. It's easy to forget what we did because it's a little abstract as usual. Same thing with Gauss's law is abstract, and then you forget what it is that you did. Okay, but in any case, we're going to end up getting this with Ampere's law, so we don't have to follow this approach. That's what happens in this PowerPoint. They start out with one method, then they later on they switch to a different method. Okay, so in this method of doing it, what they do is they start with a piece of the wire. It doesn't have to go off to infinity. So that's why they go from, they just say from A to minus A. So look, you can see this, minus A, A. So they leave it as a variable. The length of the wire is a variable, it's 2A. From minus A to A, that's 2A, too little a, right? So that A shows up in there. And then all they do is they say, oh, let me go off and do some approximation. Okay, and from that, they get this formula. So basically then what they make is they make the wire infinite. Okay, forget that. You could do it yourselves, that's fine, but you don't need to do it yourself. Because what we did is we then forgot that and we said, okay, let's just, instead of that, let's use the Ampere's law. So let me remind you very quickly. Okay, anyway, I'm gonna go off this. I'm gonna derive, using Ampere's law, I'm gonna derive again for you this one just to remind you what we did. And then we'll use it. And I'll remind you again that there is another right-hand rule that we ended up using that's made up. It's just to make it go faster. It doesn't, the only right-hand rule you really need is for cross products. That's the cross products show up all over the place. You know, they're here, they're there, they're everywhere. Okay, so they're in the force formula, and now they're in this Biot-Savart formula for the B field produced by moving charge. Okay, so that's the one you really need. But then we came up with another one. Okay, let's end here and say, okay, we're gonna rederive this thing, and I'm gonna remind you of how we could do that using Ampere's law. And then I will use it with two wires side by side. And then you will try to see if you remember how to do everything. What are the directions of the B fields? What are the directions of the forces? And then are the forces attraction or repulsion? Okay, so do everything. Now that's in the PowerPoint, of course, but let's do it without the PowerPoint at this point, okay? So the first thing we have to do is rederive this again. Make sure that this is, that's why I'm going slow here. I didn't want to just rush through it and then just assume that you knew how to do everything. Okay, so since it's gonna show up in the exam, I'm going super slow. Okay. Okay, so wires side by side. Okay, so this would be, it doesn't matter. Okay, so we have two wires side by side, and let's assume the currents are both in the same direction. Now, the first thing we have to do is figure out what direction is the B. You can choose, you have to be a little careful. Let's label everything properly. Okay, let's label it, because again, it's not that it matters. It doesn't matter whether you calculate the B field of wire 2 or the B field of wire 1, and the force of wire 2 or the force of wire 1. It doesn't matter, because whatever force is in one wire, the other wire must have the same force but opposite direction, because that's Newton's third law, action-reaction thing. So of course it has to work here as well. So if wire 1 pushes wire 2 in one direction, then wire 2 pushes wire 1 in the opposite direction with the same amount of force. Okay, anyway, so there is no real reason to do both, but we can do both just to see how it works out. It's just to make sure, absolutely sure we know everything. But let's just call this one wire 2. And we'll try to be a little careful with the notation, but it really doesn't matter in the end. But anyway, let's be careful with the notation just for conceptual reasons to make sure everything is very clear what we're doing. So there's wire 1 and there's wire 2. So the first step would be I want to calculate the force between these two wires. Okay? So the first step would be to calculate the B field of one wire at the location of the other wire. Okay, so how would I do that? Well, you can start doing integrals, but what we're going to do is go right to that formula. We're going to use this formula, obviously, for the B field of one wire. Now, since I'm using the formula, let me tell you again, let me just for 1 second derive it all over again using Ampere's law. It's not hard, but it's just easy to forget what it is that you did. But the law itself, deriving that is not hard, no. So you do this, you say, oh, what is Ampere's law? Well, Ampere's law, you gotta change it, choose a loop. Just like you chose a surface for Gauss's law here, you don't choose a surface, you actually just choose a loop around some current. So by that, that's why there's that showing up in the law. When you look in the formula in the book, that's what it shows. That's why it shows, because you gotta close the loop. You go around the current and then you close the loop, you end up where you started. And so that's why they draw that in there like that. Then you take the B field and you dot it with DL, which is an element of the wire, just like we were doing DL up and down the wire, DL being a piece of the wire. And then that must be equal to mu0 times I, which is the I enclosed by your loop. Instead of charge enclosed, here we're doing I enclosed. And instead of a surface, here we're doing a loop. So this is like a one-dimensional thing, not a two-dimension. Surfaces are 2 dimensions, loops are 1 dimension. Okay. Now there is a dot in there. Okay, but it turns out that in this case now, by symmetry, okay, good. I thought it was stuck again. Okay, so now by symmetry, so here is, now I'm gonna draw the current. So the current is coming out of the computer screen, so I just do a dot. That's my current. So this is not the same view as the wires here view. This is a different view because it's easier to draw the loop in this one. So I'm kind of looking at it from the wire itself. The wire is coming at my eyes in this view. So it's coming out of the computer screen and it's taking current with it. Okay, so since this is a wire, and by symmetry, what people do immediately, they just say, well, by symmetry, it's obvious that if I go around this wire at the same distance from the wire, r, little r, then by symmetry, it's obvious that the B field is not going to change at this location, or this the magnitude of the B field is going to be the same here, or here, or here, or here, or everywhere else. Now, based on my knowledge of the B fields, I know also by symmetry, because this wire goes to infinity, that the B field will point. Actually, I know exactly what direction it's going to point, so I'll just draw the correct direction because I have my right-hand rule. So I put my thumb in the direction of the current, and my fingers curl in the direction of the B field. So as drawn from this angle, the B field will look like in the direction of the current, which is coming out of the computer screen. My fingers curl in the direction of the B field, so it will look like this. That's the B field. At every point is tangent to that circle, and the size of the arrows stay constant because that's the same distance from the wire. So the size of the arrow shouldn't change. And it goes counterclockwise because of the right-hand rule. What right-hand rule I use? Remember, there are 3, and the first and the third are the ones that we're going to use more often. This one is kind of useful. It allows you to figure out what the B field is doing pretty fast. Again, the B field is in the plane of the computer screen, and the current is coming out from the computer screen. Okay, so the angle between the B field and current is 90 degrees. The angle between B and L, DL is a little chunk of this loop. That's DL. So since the B field is always tangent to the circle, that dot equals 1 in this situation. because the B field and the element, the little element of the loop dl, that's the L right there, is a differential piece of this loop I'm making around the wire. They're in the same, they're parallel. At each point, they're always parallel. So dot equals 1. And the B field is constant, so I can take it out of the integral. So this is what we did last time. I'm just slowing down to make sure you got it. I mean, it seems, as usual, it seems like I'm not doing any work, and yet the formula comes out correct. So what we did is we took the B field out of the integral because that's constant in this loop. It's the same distance from the wire by symmetry I know is constant. And the dot equals 1, so I just forget the dot. And then I take the integral of dl around the loop with a distance r from the wire. So this is the wire there. Okay, hopefully, I'm sure I did say that, but hopefully you didn't miss that. That's the wire. It carries current into your eyes. And that's equal to mu 0 I. Well, when you go around the loop, you pick up 2 pi r from the circumference of the loop. 2 pi r is the circumference of the loop. So B equals 2 pi r equals mu 0 I. So therefore, B equals mu 0 I over 2 pi r. Okay, maybe you already knew this, but I'm just making sure. Okay, so that's this formula. Okay, so now that tells us, now this is one drawing, and I drew the direction of the arrows. Now let me start asking questions. Let me erase this, okay? So this is fine, there's nothing wrong with this. This is in the PowerPoint, by the way. As it usually happens with these kinds of things, all the work, notice what's happening with these things. And then we can just move on, and that's it. All the work is really being done by the assumption. You're not really doing any work. The assumption does all the work for you. The assumption here is that the wire is infinite. And that's pretty much it. Okay, so given that assumption that the wire is infinite, then if all the other things follow, the symmetry of the wire and everything else, so the B field cannot change if you're here or here because it doesn't care which side you are. And then since it's infinite, then the B field points in the direction of L, dl. That only happens if the wire is infinite. If the wire is not infinite, then it wouldn't happen. So the dot would not equal 1 in that situation if the wire were not infinite. It would depend where you are in the wire at that point. But since the wire is infinite, as you go along the wire, it doesn't matter where you are because it's infinite. It's the same in both directions. It doesn't matter which location you choose to calculate the electric field. Okay. Okay, anyway, so that's what went into that. You didn't do any work. It's just all the assumption of infinite wire, and then you end up getting what you thought you were going to get. Okay, so we don't really need to use it for the first part. Let me erase this. That's just the derivation. Okay, now we're back to this. So now let's try to see if we all agree on everything here. And it would be better if I don't just say everything, just so that you don't forget how to do it at the time of exam. It's better if you try to do it. So let's be careful again. It doesn't matter which wire you choose for what, but let's just be careful on notation. So I'll spell out what I mean by the notation. So I'm going to calculate B21. So what I mean by B21, let's call this the B field of wire 2 at the location of wire 1. And we're going to call that, say, R or D, I guess. Okay, so that would be B21. Now I would like to also calculate F1. So F1, and let's forget the 2 part, if F1 is the force on wire 1. I guess it does matter. Well, no, it doesn't matter. Okay, the force on wire 1 due to the B field of wire 2. Okay? That's it. So first, let's try to see if we agree on the directions, though. I am stuck. Sorry, I'm stuck. I have to. This keeps happening every so often. It's not that hard to fix, but I have to end the process and then do it again. I mean, log in again. It won't take me long. I think that should do it. Okay. Okay, cool. That didn't take me that long at all. Okay. Okay, so great. So let's now, please, let's see. I'm gonna wait for you guys to give me the answer if you can. Okay, so just based on what, again, it can get a little confusing because you gotta choose something, but in the end, it doesn't matter what you chose. What matters is there is one thing that matters. We gotta call this current 1 and current 2. Let's just do. It doesn't. They don't have to be the same current. There is no law of nature says both wires have. So let's call this 1 and this 2. So if we're calculating B21, if that's what we're calculating is the B field of wire 2 at the location of wire 1, then what we would like to do is use the B field of wire 2, so it's the current of wire 2. So if we're going to calculate that, then we need wire 2 for that. Right? Okay. I mean, I suppose there is some problem I could give you. There would be some problem I could give you where it would matter how you do things. Here, for this expression, we're going to get the same thing as in the PowerPoint, and it doesn't matter whether you choose to use first wire 1, the B field of wire 1 to begin with, or the B field of wire 2 to begin with. It doesn't matter. But let's do 1, and then we can compare with the formula in the PowerPoint. See if we got the same thing. Okay. Right, so first question, please tell me, again, I'm going slow, but the goal is for you to tell me. Now, I'm calculating the B field of wire 2 at the location of wire 1. What direction should that be? So I'm interested in figuring out what is the direction of the B field of wire 2 at the location of wire 1. How does that work? Is this right-hand rule where you put your thumb in the direction of the current, and your fingers wrap around the direction of the B field. So if I'm doing this for wire 2, sorry. That? Yeah, no problem. Of wire 2, sorry. Thank you. Okay. So again, should we go back to the PowerPoint so that you see it visualized in the PowerPoint? I think the best idea is not to do that just yet, to do it after we get a result. So again, let me tell you the right-hand rule. Here's the wire. Okay, now this is wire 2. Okay? Now, in order to know the B field of this wire, we came up with a different second right-hand rule. Well, actually, it was the third. In the way we were doing things, it was the third. The first one was just for the cross product. Then for the direction of the B field, this is what we said. You take your wire, this pencil, and you put your thumb in the direction of the current, okay? And then your fingers, as they curl around the wire, they tell you at each point in space, right, Emma, but right. What you're saying is correct, but let's go one at a time, though, because otherwise it gets confusing. So right now, the only one we know is that we need to know that the B field at the location of wire 1. That's what you're saying is correct, though. If we were calculating the B field at the location of wire 2, it would be the opposite. But let's just stick to one of the two. So we say we take wire 2. This is wire 2. And I go, and where is wire 1? Well, wire 1 is over here. That's my finger is wire 1. The pencil is wire 2. So what Emma said in the end is what it is. But let me make sure again. Okay? So this is wire 1. This is wire 2. So I put my thumb in the direction of the current. So that's this, like this. And then my fingers wrap around the direction of the B field. So the B field keeps changing. We did that at the bottom. I just erased it, but it's okay. The B field keeps changing depending where you are. So if you're interested in here on this direction, then this would be into the page. If you're interested here, it would be to the left. If you're interested here, it would be out of the page. Well, that's where wire 1 is here. So I want to know the B field at the other wire, not some random place in space, because that's what I'm interested in, the force on this wire. So therefore, I need to know the B field of this wire at the location of the other one. Okay, I hope that's clear. That's important. Emma had it right. I'm just, as usual, when it's in the exam, I really go, I spend as much time. Sometimes it may be counterproductive, maybe to spend too much time, but let's do it. So again, is the B field, the current goes like this, and the B field at the location of the other wire, you see, is wrapping around. Here is in that direction. That's not what I need, though. I need the B field here at the location of the first wire. So that my fingers indicate that's out of the page. So that's what Emma said. So I'm going to put that in the drawing. Okay, that's no problem. That's fine. So I'm interested in the B field at the location of wire 1 because I'm calculating the force on wire 1. So that at the location of wire 1, the force comes out of the page. The B field, sorry, not the force, the B field. So I can label it like that, dot meaning out, and then I say B, as in B field, and then I could say 2, 1, just because that's what I called it. Okay, so now I already know the direction of the B field at the location of wire 1. Now I want to calculate the force on wire 1, right? To calculate the force on wire 1, I don't need wire 2 anymore. I'm done with wire 2. Okay, I now know the field, so why do I care? Okay, the only thing I care is the distance, I guess, so let me leave it there. But I'm saying once you know the B field, wire 2 is done. The only thing wire 2 gave you is the B field. Okay, the magnitude of that B field is equal to this, and D is the distance, so you would put a D in there. Okay, now the force. How did the force go? Okay, well, now you have to remember the force formula. Okay. So the force formula went like this. It was that the book has it, the PowerPoint has it in a different way that I like to write it. Okay, so let me remind you again of that. It's a little confusing, not too much. The PowerPoint has it, they turn the wire into a vector. I like to write it that the current is the vector. It kind of makes more sense to me to say the current is the vector instead of the wire, but it really doesn't make any difference. Okay, so it's the same thing, but I'm going to write it my way because I just like it better. But you can rewrite it the PowerPoint way. My way would be to say Q times L, the length of the wire, and then I cross B. Okay, so I take the direction of the current and I cross it into the B field. Well, let's do that again. Let's do that together. Okay, so I gotta here there. So sorry, oops. There is no Q here. Sorry, that's for the charges. The current is always positive. The flow of positive charges. Okay, so let's do that. And let's see if we agree. So in this case, I would be up, right? Then you're doing cross B. Well, B, what direction is B? B is out of the page. We just drew that. Emma had it the right way. So up is the current for both wires, but certainly for wire 1. Then out, my fingers now point out, and now my thumb points in the direction of the force. Okay? So what direction is the force? F1 would be in that direction. Okay, now I want to calculate what is the value of that. Well, I didn't give you L, so let me calculate F over L. Well, you have, notice what happens is, what is this I that goes in here? This I was the I2, the I of wire 2, but the force depends on the force F1 depends on the I of current 1. So if I ask for F1, then I have to put a 1 in here, right? So then force per unit length of the wire. I could give you the length of the wire, 1 meter, whatever, and then you just put it in the value. But right now, let's write it like this. Then I would have mu0. Now, notice that the cross product, by the way, there's a 90-degree angle, so that's why I dropped it again. So this keeps happening in this class. The crosses end up being 1 or 0 because of the way we do the drawings. It doesn't have to be in general, of course, but it just makes it easier. So in this case, the cross equals to 1 because the I and the B are perpendicular to each other. The I is straight up. The B is out of the board. There's a 90-degree angle there. So the cross, I drop it. Then I say mu, and then it's I1 from the force, and then I2 from the B field, from there. And then divided by 2 pi d. Okay? So you can tell what's happening here. The force on Y1 depends both on I1 and also on I2. So you can convince yourselves of this, it's not that hard. But of course, if I ask what is the force on wire 2, then let's do it fast. Emma had already gotten started it, so let's go fast this time because we already did. In that case, we would be interested at the B field on wire 2, and that would turn out to be due to wire 1. So that would be like, I have wire 1 and I'm interested over here. So this is my thumb is wire 1. Moving up, my fingers point into the computer screen at the location of wire 2. Now we're doing wire 2. Okay, so the B field would be into the board over here. That would be the B field. It would be 1, 2. And then the direction of the force would now be up into the board to the left. So it would be like that, F2. But the magnitude of it, so it would be opposing. So these two wires are attracting each other. But the magnitude of it would be the same because it would still be mu0 I1 times I2 divided by 2 pi d. Well, that's not surprising because, again, Newton's third law tells you that it's action-reaction. So that if one is exerting force on the other one has to be the same magnitude but opposite direction. So they have the same value. F2 equals F1. And is equal to mu0 I1 I2 over 2 pi d. Okay? Okay, hopefully that makes sense. Let's go back to since this is in the exam, let's go to a PowerPoint, see if the drawings are making sense. Remember that I always do drawings in the exam. This is the kind of drawing you're going to be faced with. I'm not going to use three-dimensional drawings. Okay, I'm just going to use flat and then in and out of the board. That's what I'm always going to do. This just makes it easier for people to know what's going on and to agree on what the drawing means exactly. So no debates about what is the angle here. Where are you talking about? Is that 90 degrees or 27 or 2 or whatever? If you do a 3D drawing, of course, you're always distorting the angles. Then you can get into debates about what the angles are. When you draw it like this, there is no debate. Let's go back to the PowerPoint though, just to visualize it a little more. And see if you agree that's what they ended up doing. Okay, right? So what they did in this case is they take this wire and they calculate the B field due to this wire at the location of the other wire. Okay, maybe they do a better drawing right here. Same thing, but maybe a better drawing. Okay, so you can tell that the formula they got is the same one. Now let's see again, I'm not sure that this these 3D drawings help that much, but I think you can agree with me that the drawings they have is the same one I did, but from a little slightly different perspective. They're trying to give you like a 3D feel, but it's the same thing, right? So if I drew it my way with the same, it would be like this: one wire, the other wire. The currents would be this way, that way. That would be flat. And in this drawing that I'm drawing at the bottom, then the field due to wire at the bottom wire at the location of the first wire, the top wire, would be out of the board, like that. And for the B field of the top wire at the location of the bottom wire, that would be into the board, like that. Now here, the one they're drawing is this one. They're not really drawing that one. So let's erase it because it doesn't match up with what they're drawing, right? They're drawing the B field of the bottom wire at the location of the top wire. And from that, they can calculate the force on the top wire. And it's down. So the two wires are attracting each other. So they attract each other when the currents go in the same direction. They repel each other when the currents are anti-aligned, one up, one down. Okay, any questions about that? Please ask me questions. This is in the exam, so I'll stop a little bit longer here. But you can see the formula is the same. They just mean I and I prime is just I1 and I2. Okay, are we good? Okay, let me see. We still have a little bit more time. Let's do, let's go back. Let me set up the problem and let you think about it a little bit instead of me doing everything. I'll feel a little bit more comfortable if you try it first instead of me telling you how to do it. And then we can debate whether we got it right. Here is my second example. This is the one I said we were going to do, so let's do it. And this one may also end up in the exam, actually. The formula we were just using, it doesn't have a charge. It's just the current, and great. This one is when you're given charges, which is the same. A moving charge is the same thing as a current. But it's useful to use this formula instead of the other formula because it's more applicable to charges. More directly applicable to charges. So here is my question, and then you tell me, okay, so based on this formula here, okay, this is the one we need. This is the one we're going to use. What we'd like to know is, we're going to do the same thing we just did, but with charges. So my first question will be this. Okay, so I'm going to have a specific question for you guys, and I'll give you a little bit of time to think about this and see if somebody comes up with the right answer here. First part, I have two protons. Let's move them at the same speed, velocity v. They have to be moving. If they're not moving, they don't produce a magnetic field, okay? And velocity, so let's separate them by that some distance d again. And these are protons, right? Now, here's the question. Now, the protons repel each other. You already knew that. That's the electric field. Okay, so let's remind ourselves about the electric field. The electric field is kq squared, because they're both protons, over r squared. Now, what is the direction of the force? Well, they repel each other. So on the bottom charge, the electric force will go like that. Well, you can call it electric for electric, yeah, if you want, or just call it big E, better than little e, I guess. That's the electric force. Okay, so first question is, that's the electric force on the bottom particle. First question, based on this formula, what is the direction of the magnetic force? That's not going to be that easy, right? You got to do two pieces here, but you can do it. So you need this formula, and you need another. What was the other formula for the force? So you have the B field, but to figure out the magnetic force, that's what we want to know. We need this one, sure, but we also need this one. Q, V, cross, B. That's the one we started with. That's the one where, remember when we were talking about, putting a charge in a magnetic field and making it go around and around? That's the force we used for that. This is the force on a particle moving in a magnetic field. Okay, so my question, you're going to have to use the right-hand rule twice, I guess. I mean, you don't, yeah, you should use this right-hand rule twice. My question, think about it a little bit. I can, of course, you know, I can walk you again through it and then tell you, well, that's the same thing. Direction is the same thing as a current in that direction. So, of course, you could figure it out just thinking like a current. You can also figure out the directions. But the question is very clear. The question is well posed. should I, in this drawing, where I have two protons and they're moving in that direction, in what direction should I draw the magnetic force? In this diagram, what direction should the magnetic force be in? For the bottom particle, since we already chose the electric force on the bottom particle. So let me write it down. Direction of B field for bottom proton. No, the B field first? Yeah, sure, let's do both. And then direction of magnetic force for the bottom proton. Okay? So if anybody figures it out or they think they know, just label it like answer 1, and then you tell me the direction. Up, down, left, right, in, out. You know, those are the choices. And then for part 2, same thing. Up, down, left, right, in, out. Which direction is the magnetic force? So again, you can figure that out with these two formulas. There are two cross. You could use the right-hand rule twice because there are two cross products. Okay? So once you think you know the answer to that, then you let me know. If you don't quite have it right now, that's fine, but let's make sure that you get it, though, but at the latest by the next class. So I'm still going to give you a little bit more time because, again, I know that this will show up in the exam. So if I just do it, I feel by the time of the exam, you probably forgot what I said. Maybe. So when you think you're fairly confident of the answers, the direction of the B field for bottom proton due to the top proton, and then the direction of magnetic force on the bottom proton. Once you know that, you let me know. You just put it on the message. It's 1 and then 2. Let's see if we can agree. Okay, I'll be right back. Okay, good. Isaias is kind of like trying to figure out with wires. That's one way to go. Wires are kind of easier in the end than thinking of R hats. So Isaias has the right idea there. Now, let's look at this formula and then do the R hat business again. But you don't. Isaias is talking about wires instead of charges. Well, again, that's what I said before. That yeah, you can do that. You can think of the moving charge. If it's a positive, the only thing that can get you screwed up is that I say moving charge, there's an electron, and then again you forget that the electron has a negative charge. So that makes a difference because there is a charge right there. So if it's an electron you're talking about, you introduce a negative charge. So again, current is the flow of positive charges. So the way Isaias is thinking of it is like, oh, forget that they're protons. I think that's what he's. Okay, so there's some disagreement there. Anybody want to break the tie? Okay, so let's do that part, Trent, just your part, which is if you agree with so we just said Isaias said B points into the page. So let me draw that with our usual notation. That would be at the bottom charge. B points. Oops. The B field points into the page, so that would be a cross like that. So now you're doing Q V cross B. So B cross B, and my thumb is right. So I'm doing now for once you agree that the B field is into the plane, into the computer screen, then the velocity is to the right. My fingers now point into the computer screen, and my thumb points up. Right, Trent? Yeah, let's think about, again, you can do the right-hand rule, but then at the end you can say, okay, did I pick a direction that's perpendicular to the velocity and the B field? Yes or no, right? When we are done with the right-hand rule thing, we have to have picked a direction that is perpendicular to both. And the only thing that depends on, so it couldn't be to the right, to the left, that's not. So it could be up or down, that's perpendicular to the velocity, and it's also perpendicular to the B field, right? And then in this case, the right-hand rule tells you that it's up, not down. Okay, so what you just said is, and I agree with, is force, the magnetic force is up. Okay? Now, let's go through, make sure that we all agree also on this little cross. So you could, again, you can go use these formulas. There's nothing wrong with these formulas, but R hats usually bother people. You know, the R hat in this case would be directed from the top particle to the bottom particle. But again, you can just do what Isaias is clear. Isaias, that's what he was thinking, because he's talking about wires. It's okay, no problem. Just think of the moving positive particle as a wire. So that's moving in this direction, right? And now I put my thumb. Can you see? Is it coming out in and out of view? I guess. Yeah, that's the bad part of the background thing. I can't do it very well. Anyway, you can see my finger. So I'm putting my thumb in the direction of the pencil, and that's not that great. But I'm putting my thumb, and my fingers are curling into the computer screen at the bottom. So I'm using the top particle to calculate the B field at the bottom particle. So my fingers are into the computer screen at the bottom, and they would be out of the computer screen at the top. But I'm calculating the B field of the top particle at the location of the bottom particle. So into the computer screen is correct. And again, you don't have to think of it like particles, you can think of it like wires. Well, if you think of it like wires, we're right back to our wire example that we had right there when we were doing two wires and I drew it like that. So that would be at the top wire, it would be out of the board. At the bottom wire, it would be into the board. So this drawing completely agrees with what we just did for particles. It's the same thing, right? Because we're calculating the force on the bottom particle. So that would be the bottom thing. Okay, so this agrees with the top. So yeah, as he did, he's thinking of it like wires. Go ahead, do that. Maybe that will make it easier. But you have to remember that that's protons. If you do electrons, you got to reverse stuff. Okay, anyway. You see the Q is here, but the Q is also here. So I could try to mess with you by just reversing everything and asking you the directions of everything. So, if it's an electron instead of a proton, then I have to multiply the force by a minus and also the B field by a minus. Okay, now final question. We're kind of running out of time, but I still want to do one more. We're not going to have time to go into the test bank. We'll have to do that next time. So notice what we just said here. So this is correct. This drawing is correct. Please look at it yourself, see if you agree. But it is, so it's into the bit. So the magnetic force would point up. Well, in that case, oh, actually, I should move on to solenoid. Let me just make one more point here, and then move on to the solenoid. Very briefly, say one comment about that, but I'm not gonna get into it too much. Okay, so one question you could ask in this situation where you have to you can see the magnetic force and the electric force are pointing in opposite directions based on what we just said. One is the magnetic force is pointing up, the electric force is pointing down. So you might consider, oh, is it possible that the magnetic force will exactly cancel the electric force and then there is no force? Is that possible to do? And I'll leave it to you as an exercise, but it's easy to check. You just put in the forces formula, you put in the B field formula, you put in the force formula, and then you say equals the electric force, which you already know is that's the one I just had it here before, it got erased. It's QE, and so it's, the electric is Q squared over R squared. That's the electric force. Okay, so is it possible for the electric force and the magnetic force to cancel? And the answer is only if the velocity of the particle equals the speed of light. Because the speed of light can be written in terms of mu0 and E0 square root, okay? So you can just do it yourselves as an exercise, but only if this were true, would the magnetic force cancel out exactly the electric force. But no, particles cannot go at the speed of light, so that cannot happen. You cannot cancel out the electric force with the magnetic force, exactly, no. Okay, anyway, now let's just look at the solenoid for 1 second here. And I'm going to run out of time, so I don't want to. I just want to tell you what's going on here a little bit, and then we'll. This is yet another one of those examples where you seem to not be doing anything. Now, here in this PowerPoint slide here, what they're telling you is they're trying to tell you, look, we can use Ampere's law, not just for outside the wire. That's this formula. We already have derived that formula. That's the same formula we used above for the force of one wire, the B field of one wire on the other wire. That's that. But remember, when we were doing Gauss's law, we could also go inside spheres, inside of things, and figure out what is the electric field inside. You can do the same thing here. And they're telling you here that that they can use Ampere's law to calculate what is the B field inside the wire. And it comes out to this much. Now, that's one example of something I'm going to run out of time and I can't do. But the one that we're going to use later on for RLC circuits, okay, the L in LC circuits is basically this. Okay. So yet again, there's a big assumption that that this is wrapping around, this wire is wrapping around, and then and you're assuming that you can ignore the edges. Just like in capacitors, you're thinking of it like an infinite plate that's separated by a small distance, and you can ignore the edge of the plate and assume that it's symmetrical and the field is constant and blah, 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 blah. Likewise here, you're ignoring the edges. So you're saying, okay, forget that. In that case, basically, when you're outside the solenoids, the B field, so these are like, you can think of it like individual wires. We already figure out individual wires, right? So I can calculate the B field due to this wire, that wire, and see what happens with the contribution from above, and it turns out that it comes out to 0. And inside the solenoid, they're trying to tell you that roughly speaking, of course that couldn't be true because at the edge, that's not possible. But roughly speaking, when you have a bunch of, you can think of it like individual, like a current sheet, like an infinite number of wires coming at you, and try to calculate using Ampere's law what the B field would be inside. So they end up not doing much work. This little n, I'll derive, I'm running out of time, so I'll derive this next time, but this little n means the number of turns per unit length of the solenoid. So how many times it goes around per unit length of along the axis here. That's that little n. It's a definition, just like we were doing, just remember when we were doing capacitors, we did sigma for a capacitor. Well, this little n is like the sigma of the solenoid. It's not quite the same thing, but it's a definition to make the formula look pretty. Okay, we totally run out of time. I'm still, even next class, I'm still gonna go. I would like to start a class, maybe doing this, finishing this up, polishing it a little bit, but then going to the test bank. I'll pick a few examples. I won't be able to do the whole test bank. That's too much. But I would like to please practice for the next class this right-hand rule business. My feeling is, I don't know for sure, but my feeling is some of you know it and some of you don't know it. So please try to practice it for next class. I'll pick examples where you just do a few times the same thing. But it would be nice if everybody agreed on the basics of the right-hand rule for the cross product. Okay, all right, see you guys next time. I'll try to do a little bit more practice yet. I don't think we're quite there, but by the end of next class, hopefully we will be there.